And today I have something a little different. Today I was going to actually show you, it's not exactly useful I guess, but it's aesthetic. I was going to show you how math shows up in some of artists' work. In fact, there are some artists who are not mathematicians at all, but who like the beauty they see in mathematical graphs and forms, and they've actually created sculptures and other artworks out of these kind of interesting equations. So I was going to show you a few examples. If you hunt around on the web, you can find a ton of examples, especially computer generated. But I was going to actually try and show you some actual real artistic sculptures people have created. So for example, to get you started off here, I'll show you a computer version first on my computer. This is a surface called the Boy surface, and that's because the guy that found it, his last name was Boy. And this you might find interesting because a few weeks ago we actually did an episode talking about a Mobius strip and a Klein bottle. The interesting thing about those was they were one-sided surfaces. Well, this is another one. So this surface has only one side to it. And that seems weird because if you look at it, it seems like there's an inside and an outside. But if you look carefully at the surface, you could actually, let's say this was a gigantic surface and you're running around on it, you could actually take a little jump down this tunnel right here, and you would actually be on the inside of it, but then you could keep wandering around the inside, and all of a sudden you'd find yourself on the outside, and you would never gone over a crease or a seam. Here's another view of it if you want to get another idea of what it looks like. So some artists found this kind of interesting, and they've actually created a couple sculptures of it. So I'll show you one. This is not the best picture, but this is a sculpture that was created. This is in a courtyard somewhere that is actually that surface, and they made it kind of see-through so you could see through the whole surface. I've got a couple of shots of it. Maybe, let's see, maybe this one's a little nicer. So, they just created a sort of metallic sculpture out of it. Someone else made a similar sculpture out of stone. This is actually in a garden somewhere. And it's not quite exactly what you saw in my computer version, but it's actually pretty close. I'll show you another interesting one that I found, and I'll show you the equation as well. This is, let's see, this is called a gyroid. And if you look at the equation up top, it is 3D, so this is you wouldn't actually play with this until a third semester calculus, but it's just a combination of trig functions. And yet it creates this very interesting looking surface that's really wavy and repeats these patterns over and over. Well, there's an artist that's created metallic sculptures precisely out of this equation. In fact, if I can, I will show you, here's a version of it, I will show you how this lines up. So this is an artist's creation, and let me see if I can line these up for you. This is going to be a little tricky, okay? But if I can do this, I'm going to show you how the artist got this out of this particular graph. So hold on. I'll try and shrink this. Here's the computer-generated one I have. And I want you to look at, if we can, is this version here. So hold on, it's going to be a little tricky. Let me get rid of that guy. All right, so here we go. So look at these two things, and I bet you if I tried, I could probably rotate this just right, you can see exactly that metallic sculpture. And in fact, there's another view I have of this sculpture if you want to look at another one. This is the same surface, and if I bend this just right, I bet you can see how that sculpture happened. So this is made out of metal, and in fact, if you want to buy this, if you think it looks cool, I do actually, but I got to tell you, they're not cheap. But anyway, if you want to, the person that designs these has a website, and his name is Bathsheba Grossman, and it's bathsheba.com, and you can buy all kinds of objects created out of mathematical equations. And I'm not sure how large they are, but they are, I don't know, $300 or $400. So if you want to check them out, that is, I'll show you, bathsheba.com. You can see all these sculptures that are created. I've got a couple more interesting ones I can show you. There's one it's called Enneper's surface, and this is what the surface looks like. Now the equation isn't that bizarre. It's parametric equations, which might not mean much to you, but the surface is kind of interesting. It kind of cuts through itself. And some artists have liked this shape, and they've created some similar type of sculptures. I'll show you a couple I have. This one is a similar shape, and the funny thing is, this is made out of snow. And if you look, these people actually won a prize. So they created a mathematical surface sculpture out of snow in some competition, and they won. I don't know what was the first prize. I can't remember what a red ribbon means, but they actually won a prize out of this. There's a couple other versions of this I can show you. So well, actually, let me show you one more. I'll show you some other snow sculptures in a second. There's one more I can show you from our list here. This is, let's see, I think I have a sculpture of it here. This is called a Costa surface. Here we go. So this guy, this is an example of what's called a minimal surface. Mathematicians find these interesting because they have certain properties about minimal surface area for certain shapes. But it's a kind of an interesting form, and sculptors have created a whole bunch of versions of things based on these surfaces. The equations are a little weird, but they were able to create these sculptures out of them. And I have a few examples here. This is another similar one. It's not quite exactly the same surface. That's actually created out of brass. This one, I believe, is also brass, a similar surface again. This one is made out of some sort of metal, and it's not quite exactly the same as the other ones, but again, it's kind of similar. And here's another one of this one made out of snow. I don't see any ribbon on this one. Maybe they didn't win a prize, but they made this. And by the way, these are very large. These are taller than a human, these snow sculptures they've created. I don't know how they make these things. Here's another view of it. So again, it's kind of similar to the surface I showed you a minute ago. And let's see, I got some other just kind of interesting looking sculptures for you, some more snow ones. This one's very intricate, and it's kind of related to some of the one-sided surfaces we saw. And I don't know if you can see the people. There's some little people standing on the left. This thing is like 5 times taller than the people standing there. So again, I don't know how they made this thing. So here's another snow sculpture. This is sort of like a Mobius strip. It's wrapped around itself. And here's yet another snow sculpture that some mathematicians or artists created. I've got a couple other surfaces that are kind of interesting. This is a sculpture done out of wood, actually, a single piece of wood. And this is a mathematical surface related to those minimal surfaces I mentioned. This is another minimal surface. This one is cut out of stone. I think it's out of black granite or a similar stone. Again, I have no idea how they actually create these things. This one is made out of brass, I believe. It's got some mathematical form to it. I don't know if I could come up with an equation for this, but it's definitely got some mathematical symmetry going on. Some other ones made out of metal for you. And this one is actually in the lobby of the Hyatt Regency in San Francisco. So if you go there, it's huge. And again, it's a mathematical form created into a sculpture. This is actually a lamp someone made out of some mathematical equations. You can buy this if you want. And another little metal one that same artist I showed you a minute ago created. These are made out of jade, and they're identical sculptures. One is out of jade and one is out of metal. And I am really not sure how they're creating these things so precisely, but they're pretty cool looking, actually. And last but not least, there is an artist in England who created a whole gallery out of equations. I mean, all he did was frame nice-looking equations. This one is very famous. It's called the Euler equation because it has the 5 arguably most important numbers in all of mathematics involved in one equation. 0, 1, e, I, the imaginary number, and pi. And yes, it's a true equation. I don't know if e to the I pi power would mean much to you, but this is actually a true equation. And if you think this is really strange, he had a whole gallery filled with these kinds of equations. And you can actually buy them if you think it's beautiful enough to hang on your wall. Again, I don't know if it's cheap or not. So. All right, so there you see a little bit of math used in art just for purely aesthetically pleasing purposes. So, and, you know, we see math all over the place, so we try and show you when we can where it shows up. So if you find these interesting, a little Google search will find a whole lot more where this mathematical stuff shows up in the art world. So, I did bring in something kind of cool to show you. I brought in, I brought in a loop of paper. You might be wondering, why do I have a loop of paper? There's actually something I showed a long time ago on our program. I think it was the very first program we did, and I talked about a Mobius strip. And I decided to bring that back in because I was going to show you, remind you what that was, because it's interesting on its own, but then I also have a 3D version I was going to show you on my computer. I can't really build one of these too easily, but I can show you some nice pictures on my computer of what the idea is. So you can do this yourself, actually, if you want to have a little practice. What is it going to suggest you do, if you like, is make a strip of paper, but don't tape together like I did on this one. Take a strip of paper, and I'm going to have you make a loop out of it. But instead of doing it like that one where I just did, you know, where you just make a normal loop, I'm going to have you put a little twist in the paper. So take your strip of paper, and this will be easy to remember if you're not doing it right now. You can do it later, you know, when no one's watching, if you don't want to embarrass yourself. No, I'm just kidding. It's cool. So you take your paper, and you go like this, make a loop, but you give it 1/2 twist, 180-degree twist. And then I'm going to have you tape these together. So I brought some tape with me. And I'm going to tape these together here. All right. So what I have created is called a Mobius strip. And the deal with this, I mean, mathematicians find this a very interesting shape or surface because it's considered a one-sided surface. And I know that seems strange because, you know, all pieces of paper you'd think of have 2 sides. So why is this considered a one-sided surface? Well, picture it this, if you were, excuse me, if you were like an ant crawling on this thing, I'm going to draw a dot here, and let's say that's you, the ant. I want you to just follow along the paper. So I'm going to take my pen here, and I'm just going to kind of follow along, and you're the ant walking around the paper, right? So I'm walking along the edge, minding my own business, walking along the paper here, and what happens, almost by magic, is right here, I have ended up on the opposite side of the paper as where I started, and yet I never crossed over an edge. So the idea is, I just walked along my path, and in a way I didn't even notice, without ever going across the border of the paper, I somehow ended up on the other side of the sheet. So they consider this having one side. It's like one continuous side that sort of wraps around itself. And if I kept going, of course, I'd wind up back on my same side, and I would keep doing this over and over. So there's some mathematical uses for this and when you get to higher level classes, because they have to be very careful on talking about surfaces that you can't differentiate the two sides from. But in the meantime, I think it's just kind of an interesting little thing to try. If you want to have a little fun with it, I brought some scissors with me. What you could do is cut this thing in half along the line I've drawn. And you know, if you do this with a normal loop of paper like this one I brought, I mean, it's, you know, nothing too exciting. I cut through here, and you get exactly what you'd expect, right? I'm cutting this in half, and what do I get? Well, I get 2 loops of paper. All right, expected enough, right? So try it on this one. So here's my Mobius strip. I have the path down the middle that my ant walked on. I'm going to attempt to cut this in half. Let's see what happens. So if you've never seen this before, try and predict what you think. I mean, are we going to get 2 loops like this one? You know, I mean, I don't know, kind of makes sense. Well, we're going to find out. So I'm cutting here along my ant's path, all the way to the beginning, and almost by magic, what happens? Well, you get 1 big loop of paper, which I thought was pretty weird. If you want to have some extra fun, try cutting this one in half again. I bet you can't guess what you're going to get. I'm not going to do it. I'm going to make you guys do it at home, because it's kind of cool. All right, so I mentioned I was going to show you a 3D version of this. Well, there is a 3D version. It's harder to make by hand, so I was going to show you on my computer what it looks like. So I brought a picture with me, and I got a couple pictures actually because they're a little bit hard to see. This is called a Klein bottle, and this is a sort of an X-ray version of it. I don't know if you can tell what's going on here. I have another picture that might be a little more helpful. This is a 3D rendered version, and the idea is it's a bottle that does not have a definite inside and outside. I mean, it kind of seems like it does, but yet if you look at the left, like sort of in the middle of the bottle, if, you know, where you might have liquid, the idea is the liquid could flow up through the neck to the right and flow right out the neck and magically come out the left edge again, and you'd be outside. And there's no definite seam. It's not like a glass where you would tell the edge that you're, you know, separating the inside from the outside. So in a sense, it's like a 3D version of the Mobius strip. Now the deal is here, it actually takes 4 dimensions to really picture this thing. In 4 dimensions, it doesn't cut through itself like you see here, but this is the only way we can do it in 3 dimensions. 4 dimensions, that's a whole different ball game. We'll save that for some other show. I do have a version of this that rotates, so you can kind of see different sides of it. So I mean, you can see the neck of it kind of, you know, turns around and cuts back through it. But if you try and imagine, you know, if you're walking along the edge, you could, if you were an ant walking on this thing, you could find yourself on the inside of the glass, so to speak, without ever realizing that you actually wandered off the edge. I've got another nice little video that shows you how to construct one. This is kind of how it happens. So here you have the neck, and then it just sort of gradually expands and then reattaches to itself. And that's the way you make the so-called Klein bottle. So again, the outsides and the insides kind of just blend together. A couple more pictures. And by the way, I don't want to take credit for these. These are by an artist named Tom Banshoff, I think, or Bancroft is how you pronounce his name. He does lots of mathematical art, so I can't take the credit for it. But if you want to have a little fun, somebody made one out of Legos. So I don't know how much patience that took, but there's their Lego Klein bottle. And here's a split version of it. They opened it up so you could see inside that it really does work as far as how it's supposed to. I suppose you could pour water in it and make it fall out of itself. And if you're really inclined, if you're really having fun with these things, well, people are selling Klein bottle hats. So you can go on the internet and buy a Klein bottle knit cap. I'm sure that'll make you a fashion statement on campus. So there you go. Not only do you do a little fun with paper and scissors, but you can even wear it if you want. I don't recommend using Klein bottles for beverages because they do tend to not hold liquid very well. So, but you know, if you look on the internet, people actually made them out of glass in case you want to try. I don't know. That's up to you. So this four-dimensional stuff, it's really weird, and like I said, that'll have to wait, maybe some other time. I brought in a little toy with me. This is actually a toy I had in my own childhood, and maybe some of you have seen it as well. They actually do still sell it. It's called Spirograph. I brought a box with me. This is a more recent version of it. Now, I know this looks like product placement or something. Don't worry, we have nothing to do with the company. It's just kind of a cool little toy. And the way it works is there's these little plastic discs and rings inside. Look like this. Here's a little disc here and a ring. And there's little holes in the ring, and they come with different sizes and different shapes. And the idea is you put on a piece of paper, you put the ring inside or the disc inside the ring rather, and then you select one of these little holes with your pen, and you kind of move the disc around the ring, and your pen's ends up drawing a cool pattern on paper. So we're going to do this together. I'm going to make one of these with you. And so I'm going to scoot over here to my math cam for a second, and with any luck, my pen won't slip, and we'll do a cool pattern for you. Okay, so I put the ring down on paper. Let me zoom in a little bit for you. Okay, and I just selected one of the rings, and if you can see all those little holes in there, I'm just going to kind of select one of them at random, stick my pen in there, and I'm just going to try and kind of wind this around like a gear. And I know my pen's going to be a little bit in the way of the picture, but hold on, and you're going to see a nice little pattern. I think my pen just slipped a little bit, but you'll get the idea. So you wind it around, and normally what will happen is you'll end up completing a full cycle of patterns. Something like that. Now, I was a little off. You can see a little glitch there, but that's the idea. And if you select different size discs or different shaped rings, you can get all kinds of different patterns. In fact, I made a few yesterday. I'll show you some other ones I created. They're kind of cool. So here's some other ones I have. Let's see, I'll zoom out a little bit for you. A little selection for you there. So what does this have to do with math? Well, there are mathematical equations actually controlling these shapes. In fact, it's from a type of equation called a hypocycloid. And it's done from the motion of a wheel turning along inside of a circle. And if you just keep track of points on that circle, what kind of path they leave, you end up with all these neat looking shapes. So I brought a graphing calculator with me, and if you have one as well, maybe you should grab yours. I'm going to show you equations you can use to make shapes like this on your calculator. You might not even recognize some of the equations we're going to use, but it's okay. I'll show you how you can kind of play with them and change some of the shapes that you see. So I'm going to get my calculator here, and the first thing I have to show you is we're actually going to use a different kind of graphing than maybe you've been used to. So you have a button on your calculator. If you have a TI calculator like mine, this is a TI-84, you have a button called Mode. It's near the top, and if you hit Mode, it's going to bring up a whole bunch of options. And you probably don't play with these normally, but the one I need you to change is right down here on the list where it says FUNC for a function. I need you to change that to PAR. That stands for parametric. That's a certain kind of equation, and I'll show you what it looks like in just a moment. So all you need to do is hit Enter on that one. And then if you go back to the Y equal key, if you're familiar with graphing on your calculator, you'll see a little bit of a different setup. You will see an X and Y separate listing, and if you try and type in variables, you're going to see a T, not an X like normal. Well, what this is doing is it's creating separate equations for X and Y. So instead of you having just one equation for Y, you now have individual ones, and you select a value for T, and it in turn creates values for X and Y and draws a graph. It's almost like if you had a remote control car driving around on the ground and you're keeping track of its X and Y positions. You can think of T as time if you want. So if you'd like, try and type in the equations I have on there. I know they're a little complicated, and actually you might see some things rather you don't recognize, like this little word right here, COS. That's a trig function, cosine. But you do have a button for it. So if you'd like to try and enter these in, you notice the two equations are similar. We'll come back to them in a moment if you want to try. Let me show you what this actually looks like. I'm going to hit my graph button, and you can watch my calculator actually draw this shape. If you watch the motion, it's doing it just like it happened on paper. I know it's a little jagged. Well, that's a restriction of the calculator. Your calculator doesn't have the highest resolution screen, right? But it is actually doing one of these shapes. Now, you can change some of the settings. So if you don't see this whole shape, you might need to change some of the values you see. So if you try your window key, which is normally you select how much of the X and Y numbers you'd like to see, you'll see an extra value in here. You'll see something for T. and I have mine set to go from 0 to 44. That should be enough to get us the whole shape. So I'll show you the equation again, and it might be fun if you want to fiddle with this a little bit. I know these look kind of complicated, but if you look at this number in front of the little cosine word there, this 3, you notice that shows up in both of the equations. If you change that, you can actually change what the shape looks like. So leave the rest alone, but I'm going to go in and I'm going to change this 3 to a 2, and I'm going to scroll down and do the same thing to the second equation there. I'm going to change that same 3 to a 2, and let's draw it again. You'll see a little bit of a different shape this time. So what we're doing, it kind of affects how wide the little loops are and how many times around it's going to take to draw the whole pattern. But you can get a whole variety of kind of like flower type patterns. Now you probably wouldn't play with equations like this until maybe a pre-calculus type class. You'll definitely see them later in a calculus class. But if you've just been in algebra, these might seem a little strange to you. But like I said, you can just kind of mimic what we did and copy the equations down and still get a decent picture of what the pattern looks like. All right, so let me show you the equations one more time just in case you wanted to try and copy them. And in the meantime, you can play with the numbers. I changed that 3 to a 2. You can try changing it to a 1 or even to a decimal number like 2.4, and you can get some different kinds of values. It's kind of fun. I played with the spirograph as a kid. I didn't realize there was any math involved, and it's kind of neat to see the math connection now. In the meantime, I mentioned a little earlier that I was going to talk to you about some music on a compact disc and the mathematics involved. So just for a few minutes, this is kind of interesting. I brought with me a CD. So I'm sure you're all familiar with a compact disc by now. Here's a CD. You might not realize how this disc turns into music for your ears. It actually has to turn all of your music into numbers. This entire disc is simply filled with numbers. To do this, it has to listen to the music and 44,000 times per second, separately for the left and right channels of your stereo. It has to record a snapshot of what the sound looks like. So 44,000 times a second, it takes a picture of what the sound looks like, and it uses a large number to describe that picture. And then 44,000 times per second, it just changes these numbers, and that change creates the sounds you hear in your ear. Now, how does it get on the disc? Well, there are little tiny bumps recorded into the surface of this disc, and your CD player has a laser. The laser can focus so sharp that it can focus on just one little line of these little bumps. It's actually in a very, very tight spiral. In fact, there are over 6.2 billion individual numbers encoded on this disc. Your laser reads through them in a very tight spiral. In fact, if you could unwind the spiral you see on this disc, if you could take the little line it's reading and undo it, it would be over 3.5 miles long. So it's actually amazing to me that this even works, that you can get that many numbers on this little disc and have it come out as music that sounds perfect. The question I have for you, and if you've ever had like a Walkman where you can actually see through a window on how the disc spins, it actually changes the speed it spins as it goes. That's because on the disc, the laser actually starts in the center. It reads at the very center here, and it moves out towards the outer edge. Now, what I want you to do is for a moment compare that to the old days. Do you recognize one of these? This is a vinyl record. Now, I know most people don't listen to these anymore. I still do, actually. But these worked with a little bit different technology. These are not encoded as numbers, of course. There are grooves in this disc, and a needle starts at the outside, and it again winds in a spiral, and it winds its way in. The difference here is this spins at a constant speed. In fact, this is 33 1/3 RPMs. That's revolutions per minute. So every minute, this is going to turn 33 1/3 times. Now, the speed has to stay constant, and as the needle moves through the record, what happens is on the outer edge here, it actually travels longer than when it gets to the middle. So think about it, in 1 minute, you know, how far your disc turns, your needle has to go all the way around the edge if you're at the outer edge at the beginning of the music, and towards the end, it's a much smaller area. And so actually, the fidelity here is better at the outer edge because you actually travel faster through the grooves at the outer edge than you do in the middle. Well, the CD cannot do that. Your CD player has to have a constant linear speed. What that means is the laser has to follow that really tight little track at exactly the same speed as if you were walking along the track. The speed it has to do it at is about 1.25 meters per second. That's roughly a walking pace if you were going to go outside and take a little stroll. So how do I make this disc always feed the laser the numbers at the exact rate? Well, Well, your disk has to change speeds. So when you start, the laser reads at the center, your disk actually has to turn faster than when it does at the end. If you do have one of those older Walkmans where you actually have a little window you can watch the disc, you can actually see this for yourself. Start a CD that's nice, nice full-length CD, start at the beginning and watch how fast it spins, then skip to the last song on the CD. You'll see it actually slow down. So a little math problem for us to figure out while we're thinking about this. I want to know how fast this thing has to spin in order to adjust for the speeds. So we're going to summarize the information here, and the only thing I had to do is I took a ruler and I measured how far these values go. And so for instance, we'll do a quick little version here. Let's start at the center, and I know it's about 23 millimeters from the center to the edge. So if I start here with 23 millimeters, what I want to know from you guys, so I've written down 23 millimeters. What I want to know from you is how many times per minute does this thing have to spin? And the key is to figure out the circumference. So what I want to do is figure out how far around the disk it takes in one circle. And this is related to pi. This is a formula for circumference. The circumference here is 2 pi radius. If I put in 23 millimeters, I get about 46 millimeters for my circumference. What you would do after that is turn this into meters, and then I would want you to try and figure out how many times you'd have to spin this to get 1.25 meters per second consistent speed. It turns out when your disk starts, it has to spin over 500 revolutions per minute. That's quite fast. By the time it gets to the edge, it's only 200. So it literally has to go more than double speed when it starts to keep up that same speed.